All right, the last topic we covered was the concept of torque. Okay, and best way to think about torque is the applied force times the moment arm. Okay, so we look back in the notes on what the definition of a moment arm is. Okay, and I did the example of there's a wrench. Okay, and here's a picture of a wrench. Okay, so there's a wrench. There's someone's hand. They're pushing or pulling on the wrench, and that's how we looked at torque. Okay, so I said eventually we're going to make the connection between the old stuff and the new stuff. Okay, so the old stuff, you had a force, okay, applied to a mass, and the object accelerated. Now you apply a force, right? Maybe your hand is pushing or pulling on the wrench. So now you apply a force. Okay, maybe your hand is here. Okay, you apply a force, and the object, instead of we saying it accelerates, now we say that force exerted a torque, and the object will now rotate. Instead of rotating, we say with acceleration a, we say it rotates with an angular acceleration alpha. Okay. Okay. So let's look at how we can come up with Newton's second law, okay, for rotational motion. Okay, so here's my wrench. There's my axis. Imagine I have a bolt here. Instead of one force, I have many forces. Okay, so F1 can be a hand. Okay, F2 is another hand. So I have many different hands on the same wrench. Okay, and they're pulling in all different directions. Okay, so but if I look at, let's say, one particular one. Let's say if I look at F1. Okay, remember, if the wrench rotates, let's just say it rotates counterclockwise. If the wrench rotates, what path did we say that part of the wrench is going to take? Okay, it's going to trace out a circle. And earlier we said that if that's the case, if I take F1 and I broke it up into its radial, and then I had tangential, there's my tangential component, we said that only the tangential component of the force causes a torque. So that's what I have here. Only the tangential component of each of these forces causes a torque about axis A. Okay, and that's what I had in the previous pictures. Okay, okay. So for example, there'd be an F tangential for force number 3. There would be an F tangential for force number 2. Okay, if this was force number 4, okay, there'd be, whoops, if this was force number 4, right there. So if this was force number 4, there'd be an F tangential for force number 4, okay? But instead of calling it force number 4, okay, this is the nth force. So if I have 8 forces, that'd be the 8th force, okay? So for the nth force, okay, the only component of this force that causes a torque is the tangential component, okay? So that's why I said that the torque, the ith torque due to the ith tangential force. I could have said the third torque due to the third tangential force. Okay, here I'm doing it in general. So the ith torque due to the ith tangential force, okay, so that torque is just the tangential force times that moment arm. Okay, so again, if that was my third force, it'd be my third tangential, it'd be the tangential component of the third force times the moment arm of that third force. Okay, so if I want to find the tangential, or if I want to find the torque due to that ith force, is I take the component, the tangential component of the force, multiplied by the moment arm. And remember, if these are now tangential, let's look at this thing over here. Okay, if the force is tangential, then when I draw a moment arm from the axis of rotation, okay, out to that force, then that distance is already the moment arm. Okay, so that's why my my moment arm for my ith tangential force is just the distance out to that force r sub I. Okay, so now from the earlier chapter, okay, right, F is equal to ma. So my tangential force, okay, my tangential force is mass times my tangential acceleration. Okay, so if I had my tangential component of my third force, whoops, if I had my tangential component of my third force, that'd be m3 a tangential 3. Here I'm doing it in general for an index I. Okay, so my ith tangential force is ma tangential. Okay, I'm just using Newton's second law from the earlier chapter, okay, in the tangential direction. So here's my torque. Okay, here's my tangential force, and I put in ma tangential. Okay, don't forget the index. The r still sits here. There's my r. Okay, but from the previous chapter, a tangential is r alpha. So right here where I had a tangential, okay, I put in r alpha. Okay, so a tangential I is ri alpha. Okay, and there's no index. I don't need an I, okay, on the alpha, because we saw earlier that for a rotating object, okay, every point on a rotating object has the same omega, okay, and every point in the object has the same angular acceleration. Okay, so a rotating object, there isn't an omega 1 and omega 2, and there isn't an alpha 1 and alpha 2. There's just one omega and one alpha. Okay, so that's why I don't have an index. That's why I don't have an index on the alpha. Okay, so I multiplied these two r's together. Okay, all right. So that gives me my tangential. That gives me the ith torque due to my ith tangential force. Okay, so if I want to find the net torque, I have to sum them all up. Okay, so I'm taking a sum of both sides. So I'm taking a sum there, okay, and a sum right there. So this is the net torque, okay, that's my net torque. And this, all right, I'm taking a sum over this, but there's no index on alpha, so that gets to come outside, all right. But this quantity here, okay, from our chapter, that's the moment of inertia. Okay, so I have that the net torque about r axis A, okay, is equal to the moment inertia of the object times the angular acceleration, right? And if I compare that to the previous chapter, right, we had the mass, you apply a force, and the mass accelerates, right? Newton's second law. Okay, well, just like we did rotational kinematics, where position got mapped to its rotational counterpart, angular position, okay, v, velocity, gets mapped to its rotational counterpart, angular velocity, and alpha gets mapped to its rotational acceleration A gets mapped to its rotational counterpart, angular acceleration, okay. Force gets mapped to its rotational concept of torque. Okay, here's acceleration getting mapped to its rotational counterpart, angular acceleration. And we saw earlier with kinetic energy that mass gets mapped to its rotational counterpart, moment of inertia. Okay, so if you ask someone now, what's Newton's second law? Okay, instead of giving you F equal ma, they could give you net torque equals I alpha. Okay, so the idea is old chapter. Okay, this says you apply a force on a mass or a glider, object accelerates. Now, this says you apply a torque, okay, you apply a force, okay, at some distance, so you apply a torque, okay, instead of thinking of the glider accelerating to the right, now you're applying a torque and this system is going to rotate, the wrench is going to rotate, okay. Okay, now, for a good video on that, if you click on this link, okay, go to that link, and that'll be in the notes. All right. There's a short video on a little bit more about this, with maybe some demonstrations that hopefully will make more sense of this.